topics for this week that I'm going to cover. We have like vectors, dot products, and length of vectors. Matrices, linear combinations, and row picture, column picture. And linear independence of vectors. So I guess that's up to chapter 2 in the textbook, which is the string book. So vectors, everyone should know what a vector is. It's something with a length and a direction. So there's a couple notations we use to denote vectors. So the vector 2, 1 could be those sharp braces, or you could write as a column vector, or column vector with parentheses, or you could just write it as an ordered pair. Either way, it's referring to this vector whose tip is at the point 2, 1. Nope. Sorry. Okay, thank you. Another way they like to write it is as a linear combination of these i's and j things. So those just refer to vectors 1, 0, 0, 1. So you know how to add vectors, right? So if u is the vector u1, u2, and v is the vector v1, v2, then u plus v is u1 plus v1, u2 plus v2. You add their components. Visually, this looks like this is u and v, taking u and putting it at the tip of v, and then drawing the vector from the origin to the tip of that u vector. So you can translate vectors wherever you want. You can move them around. It's the same vector. So you can also multiply vectors by numbers. So if c is a real number, does everyone know what this symbol means? It means element of. So c is an element of the real numbers, and v is this vector v1, v2. Then cv, cv1, cv2. So you take the scalar and move it inside the vector. It's called scalar multiplication. So that also has a visual interpretation. If this is u and c is like 2, and this would be 2u. It makes it longer. Or you could have negative u, or 1/2 u. So there's some basic things. We define the length of a vector. So the length of v equals v1, v2 is, you note it with that symbol or just that symbol, either one. It's a square root of v1 squared plus v2 squared. Obviously, if your vector has 3 components, then it's the same thing. If v is v1, v2, v3, then the magnitude of v, or the length, is the square root of v1 squared plus v2 squared plus v3 squared. That's the same thing, just different notation. It's just sometimes we use the absolute value notation to refer to a number as well. We use that of numbers too. So maybe you want to distinguish between those two, but it's the same thing. So a unit vector is a vector with length 1. The unit vector in the direction of a given vector. So if I give you some vector v, the unit vector in the direction of v is like v hat. Sometimes we denote it that way. It's just v divided by its magnitude. So you divide by its magnitude and it makes it length 1. So for example, if v is the vector 2, 1, the magnitude of v is the square root 2 squared plus 1 squared, which is the square root of 5. So the unit vector in the direction of v is 2, 1 divided by root 5, which is 1 over root 5 times 2, 1, which is 2 over root 5, 1 over root 5. We can also define notion of a product of two vectors. So if you have two vectors, u1, u2, and v is v1, v2, then the dot product of u and v is u dot v equals u1, v1 plus u2, v2. So you multiply the components and then add everything up. Notice that that's a number. It's not a vector. So that's a real number. There's an important geometric significance for the dot product. There's this formula, u dot v is the magnitude of u times the magnitude of v times cosine of the angle between them. So the picture is like this. That's u, that's v, that's theta is the angle between them. So from this formula you can see that so u will be perpendicular to v whenever, if and only if, the angle between them is 90 degrees, or pi over 2, which means that the dot product is 0, because cosine of pi over 2 is 0. Yeah, when I wrote absolute value, I was using that as just another symbol for magnitude. Yeah, so that you could also like write it this way if you want. Because usually the context makes it clear that it's a vector and you're doing magnitude. Okay, so let's talk about linear combinations of vectors. So a linear combination of vectors u and v is a vector of the form cu plus dv, where c and d are real numbers. They're scalars. So it's literally a combination of u and v. For example, we can, if I give you two vectors, 1, 2, and 3, 1, we can try to draw a bunch of linear combinations. We try to draw the region represented by the set of linear combinations cu plus dv, where we can do c's between 0 and 1 and d's between 0 and 1 to start with. So u looks like maybe that, v is like that. So we can put u at the end of v by translating it. So this would be the vector u plus v. But we can also make v smaller because d ranges between 0 and 1. So like this is u plus v. But we could also do u plus a half of v. So a half of v is right there. So maybe if you put u at the end of that one, you get that vector. So that is u plus a half of v. And you could use that scalar d all the way between 0 and 1, so you can get any vector here. You can put it there, you can put it there. So you get all those vectors. So basically you're getting that whole parallelogram, right? This whole parallelogram. So that's the shaded region. That's the region represented by that set. Another example would be if you take cu plus dv, where c is bigger than 0 and d is still between 0 and 1. So in this case, that's u, that's v. U is allowed to get as large as we want it to, right? Because c ranges from 0 up to infinity. So c could be anywhere, cu could be anywhere along there. It goes off to infinity. And then we can put that at any point of v to get u plus, or cu plus dv. So we could put that here, we could put that there, put that there. So any of these points we can get from that linear combination. So it's that whole upper plane there. It's an infinite parallelogram kind of thing. What about this one, where d is greater than or equal to not 0, but 1? So we draw that. So we can't get any vectors along here, right? Because that would be a scalar smaller than 1 for v, but it has to be bigger than 1. So that means that we can only get vectors starting at this point and going outward. So we might as well just move v to this point so we know that we're starting over here. And then at that point we can move u anywhere along v. We could make it longer if we want. So basically, everywhere to the right of this line here, we're going to get this whole plane. What if I did? What if I allowed c to be between negative infinity and infinity, and d to also be between infinity and negative? So what if we let c and d be any numbers? Right, it would be the entire plane, it would be every vector. So this one would be all of R2, you could say. The whole plane. So let's talk about row picture and column picture. So for example, let's say we want to solve some system of equations, negative x plus y equals 2, and x plus 3y equals 2. say we want to solve that. There's two ways they want you to think about the solution to this problem. First way is probably something which is familiar, the row picture way of thinking about it is to graph the two equations as lines in the plane. And then their intersection, the intersection of the two lines is the solution to the problem. Their intersection is the solution. So, for example, the way you would go about doing that, with this equation, you can solve for y to get y equals x plus 2. And then with the other equation, x plus 3y equals 2, we can solve for y again to get, let's see, it would be a third of 2 minus x, which is negative 1/3 x minus plus 2/3. And we can draw those lines. So this is the line y equals x plus 2. And then the line y equals minus 1/3 x plus 2/3 intersects somewhere around here, and it has a slope of negative 1/3. So maybe it looks like that. So you can see they do intersect, so there's a solution to the system of equations right there. That's going to be the solution. We just have to figure out what that point is. So the way we do that is we set the y equations equal to each other. So we set x plus 2 equal to negative 1/3 x plus 2/3. So if you multiply both sides by 3, you'll get 3x plus 6 equals negative x plus 2. And you can move stuff around, you get 4x equals negative 4, so x equals negative 1. And then you can find the corresponding y value using this equation. So if you plug in x equals negative 1, you get y equals 1. So the solution is negative 1, 1. So that's negative 1, 1. That's the solution. So another way to think about it is using vectors, which is the column picture way. Let's see, so I label that as 1 or something. Yeah, I did. Okay, let's call it 2. So the column picture expresses the right-hand side of the two equations. The right-hand side is a linear combination of a bunch of column vectors. So what do I mean by that? Well, if we take the two equations we had, x plus y equals 2 and x plus 3y equals 2, you can write this as, if you factor the x's out, see, this was negative x plus y. If you factor the x's out, you get negative 1 and 1 as the coefficients of the x's. If you factor the y's out, you get 1 and 3 as the coefficients. And then the right-hand side is 2, 2. So it looks like we're trying to express 2, 2 as a linear combination of negative 1, 1 and 1, 3, these vectors. So that means that solving this equation is the same thing as answering the question of what linear combination of these two vectors gives 2, 2. So if we draw a picture, we get the column picture. Let's see, so 1, 3 was the first vector. Or negative 1, 1 is over here. And then 1, 3 is over here. And so I want to write this vector 2, 2, which maybe that's like this. I want to write this vector 2, 2 as a linear combination of these other two vectors. Well, we already solved the system, so we know what x and y are. So xy is negative 1, 1, which means we can take negative 1 of the first column, which looks like this. So this is negative 1 of the first vector. And we can add to that 1 of the second column. To get 2, 2. So then we can add to that just the vector 1, 3. So I'll just shift it over here, 1, 3. And you can see that you add them together and it gives you this resultant vector 2, 2. So that's column picture. So in this example, the two columns that we had, they weren't parallel vectors, right? So that's why we had the two lines not being parallel, the lines intersected. So there's some other ways to, some other situations though. Like, for example, what if you had this equation, x plus 2y equals 2, and 2x plus 4y equals 8. So in this case, if you solve for y, you get, I guess it would be 1 minus a half of x. If you solve for y here, it would be 2 minus a half of x. So they're parallel lines that don't intersect because one of them looks like this, 2, and one of them looks like that at 1. So they're parallel, non-intersecting lines, which means this system of equations doesn't have a solution. But if I change this equation a little bit, like if I change the 8 and make it a 4 instead, so I had x plus 2y equals 2, and 2x plus 4y equals 4. If I have this instead, then when you solve for y, they're actually the exact same equation. So they're both the same equation, they're the same line. You get the same one twice. That was a bad line. I'm supposed to draw it like that. Same line, so that means that there's infinitely many solutions. The whole line is the solution. So there's a lot of ways you can get more than one solution or no solution. You can get either infinitely many, no solution, or a unique solution. Those are the three possibilities. And we'll see that in a lot of different ways this semester. So let's talk about matrices. So a matrix is just a rectangular array of numbers. One important thing about them is that they represent systems of linear equations. So, for example, have some system of equations. You can write it as a matrix equation just by taking the coefficients of the x and the y's and putting them into a matrix. So we have this matrix equation now. So this is like A times V equals B, where A is the matrix 1, 2, 3, 4. V is the vector x, y. So there's a couple ways to think about the product of these two matrices, and they ask you to do both on homework assignments and quizzes and stuff. So one way is to think about AV as a linear combination of the columns of A. So if you take the matrix A and you multiply it by the vector V, one way you can compute that product is by taking the x and then putting it in front of the first column. So you get x times 1, 3. And then taking the y and putting it in front of the second column. X times 1, 3 plus y times 2, 4. So that's one way of computing that product. Another way is just by noting that AV is a dot product of the rows of A with the vector V. So if you compute this product, one way we can do it is by taking this whole first row and multiplying it by the column as a dot product. So you do 1 times x plus 2 times y. And then for the second entry, you take the second row and dot product it with that vector. So I guess you would get 3 times x plus 4 times y. So it is a dot product. It's just 1, 2 dotted with xy, and then 3, 4 dotted with xy. So for example, if V is the vector 2, negative 1, if we're using the same matrix, then A times V is 1, 2, 3, 4 times 2, negative 1. So you can write that as 2 times 1, 3 minus 1 times 2, 4, in which case you would get 0, 2. Or you can do it the second way. So 1, 2, 3, 4 times 2, negative 1. You could do it like 1 times 2 minus 1 times 2, and 3 times 2 minus 1 times 4, which would give you 0, 2 again. That's two ways thinking about that multiplication. Now let's talk about solving a general equation ax equals b. So like if you have like a linear equation 2x equals 6, you can solve that by just doing x equals 1/2 times 6. Similarly, if you have a matrix equation ax equals b, where x and b are vectors, you can solve that by doing x equals a inverse times b. So a inverse is like the reciprocal kind of, because it cancels out the a. So for example, if A is 1, 2, 3, 4 like before, and x and b are just these arbitrary vectors, we can try to compute A inverse by solving the system AX equals B by hand. So the equation AX equals B is the same as this equation. X1 plus 2x2 equals B1. 3x1 plus 4x2 equals B2. Using these coefficients in the matrix. Now if we solve for x1 and x2 in terms of b1 and b2, that'll give us the coefficients of A inverse. So let's take x1, it's b1 minus 2x2, and then if we plug that into the second equation, it says that 3 times b1 minus 2x2. So I'm replacing that for x1 here. Plus 4x2 equals b2. If you solve this for x2 now, 3b1 minus 6x2 we solve for x2. This is minus 2x2 equals b2. We're going to get negative x2 equals b2 minus 3b1. So x2 is 3 halves of b1 minus a half of b2. So that's x2. Now we can take that and put it back into the equation we have for x1 and get x1. So let's see, we have x1 equals b1 minus 2x2, which is 3 halves of b1 minus a half of b2. So if we simplify that, we'll get this, which is negative 2b1 plus b2. So that's x1 and x2 in terms of b1 and b2. That's basically the solution. So now if we take that and try to convert it back into a matrix equation, we'll get the inverse matrix. So let's see, x is x1, x2, which is negative 2b1 plus b2, and 3 halves of b1 minus a half of b2. Now if you take the coefficients of the b1s and b2s, you get the inverse matrix. So you can write this as negative 2, 1, 3 halves, negative 1 half, times b1, b2. So this is A inverse times B. So that's how you find the inverse matrix. Later on there's going to be a lot better ways to compute the inverse of a matrix, but that's how we do it for now. Any questions about that process? Let's talk about linear independence of vectors. So I'll define dependence first because that's probably easier to define. So if you just have two vectors, the simplest case, we say that U is dependent or linearly dependent upon V if U is just a multiple of V. So U is C times V for some real number, some scalar C, which just means U and V are parallel. So two vectors are dependent if they're parallel. And then obviously you can define a similar thing for three vectors. U is dependent upon V and W if U is a linear combination of V and W. So C and D are real numbers. So for two vectors, that just looks like they're along the same line. For three vectors, you kind of have to draw it in 3 dimensions. So imagine I have some 3-dimensional coordinate system here, and I'm going to draw like a plane. So say this is the plane determined by these two vectors v and w. When I say that u is dependent upon v and w, I mean u is somewhere inside the plane, as opposed to this vector, which points directly upward, which is not dependent. It's not in the plane. And then to define independence, you just say a vector is independent from some other vectors if it's not dependent upon them. So u is independent from v and w if it is not dependent. Makes sense? So it's not a linear combination of v and w for any scalars. There's an equivalent definition of independence that I'll write down. So u, v, w are independent if and only if whenever you have some scalars c1, c2, and c3, so that this combination gives you 0, then c1, c2, and c3 have to all be 0. So u, v, and w are independent if and only if this implies that. And that's usually a good way. It amounts to solving a system of equations to prove that 3 vectors are independent, because you're just solving for c1, c2, and c3. Oh, sorry, that should have been equal to 0, right? So let's do an example where we prove that some vectors are dependent. Let's say u is this vector, v is that vector, and w is this vector. So let's prove that these guys are, let's say, dependent. That's probably easier to start with. So we want to prove that one of the vectors, it doesn't matter which one, is a multiple or a linear combination of the other two. So we can say w is cv plus du. We want to solve for c and w. Basically, we want to find c and w so that this equation works out. So if we write out each component separately, this means that 0 has to be 1 times c plus 2 times d. 4 is 2 times c plus 0 times d, the second component, and 5 is 3 times c plus 1 times d. So we want to solve this for c and d. Since we have 3 equations and 2 unknowns, they won't necessarily have a solution, in which case they are independent. But since I said prove they're dependent, it's probably going to work out, because I designed it that way. So the first equation says 2d is negative c. The second equation says 2c is 4, which means that c has to be 2. If they're going to be dependent, then c has to be 2. And since we have c equals 2, that means that from this first equation, 2d equals negative 2, so d has to be negative 1. So if they're dependent, then d has to be negative 1, and c has to be 2. And then we just have to check that this combination satisfies the last equation. So check that c equals 2, d equals negative 1 satisfies this equation. well, obviously 5 equals 3 times 2 minus 1. So it works out. So we can check that 0, 4, 5 is 2 of 1, 2, 3 minus 1 of 2, 0, 1. So that works out. They are dependent. We can also prove that vectors are linearly independent. So let's say I have these 3 vectors, and I want to prove that these guys are linearly independent. So we can do it the same way we did the previous problem. Let's try to write one of them, say u, as a linear combination of the other 2. And try to solve it for c and d. So we have 1 is c minus d, 2 is 2c plus d, and 6 is 3c plus 0d. So this last equation immediately says that c has to be 2. And then if you put that into like the first equation, then 1 is 2 minus d. So d has to be 1. So if they are dependent, then d has to be 1 and c has to be 2. So we need to check if this satisfies the second equation. So we need to check, does that satisfy the second equation? Well, probably not. So is 2 equal to 2 times 2 plus 1? No, it's not. So that means that they are independent. Because u is not a linear combination of v and w. Any questions about those concepts or the process? Yeah, it doesn't matter which one you pick, try to express as a linear combination of the others. Are there any other concepts that they covered in lecture that I should talk about? Or any concepts from the homework? A lot of people have asked me about the direction cosines problem. So I can try to explain that concept that might be useful. So you can, if you take any vector, u1, u2, u3, it makes some angles with the x, y, and z axes. Right, so let's say u is like coming out of the page there. So it makes an angle of, say, alpha with the x-axis, and beta with the y-axis, and gamma with the z-axis. And then the direction cosines are just the cosines of those angles. And oftentimes they'll ask you how to find those angles. Like, is there a formula or something? Well, there's only one equation that we've talked about that involves the angle between some vectors, the angle of a vector, and that's this formula we talked about earlier. u dot v is the magnitude of u times the magnitude of v times cosine of the angle between them. So if you take some vector in the direction of the x-axis, you call that v, then the angle in this equation will be alpha. So if v is in the direction of x-axis, then u dot v is the magnitude of u, magnitude of v times cosine of alpha. So you can solve for cosine of alpha. It's u dot v divided by the magnitude. And then similarly for the other two direction cosines, you can choose a vector in the direction of the y-axis to get cosine of beta. Then you can choose, a vector here. But other than that, that's all I had. So I hope that was helpful. I mean, like a set of linear combinations. Yeah, that's a good question, because there were some questions about that on the homework assignment. So in order to determine if some vectors, the set of all linear combinations of two vectors, so in general, like when we were doing the example where we were filling in the plane, we did an example where we had the set of all linear combinations of those two vectors, and it gave us all of R2, remember? So in general, the set of all linear combinations of u and v is a plane. But that's only if u and v are independent. So if they're dependent, then they won't give you a plane, it'll give you a line. And then whether or not that plane is in R3 or R4, three-dimensional space or four-dimensional space or whatever, it just depends on how many components these vectors have. So if u is like, if u and v have only 3 components, then it'll be a plane in R3, because you have 3 components. But if they had four components, it would be a plane in R4. The set of all linear combinations of three vectors. In general, if u, v, and w are all independent, then the set of all linear combinations of u, v, and w is just a space, 3-dimensional space. But it's possible that not all of those vectors will be independent. So like, you might have u and v are 2 vectors, and these are independent from each other, so they're not parallel. But w is another vector, and it's dependent upon the other 2. Then in this case, the set of all linear combinations of u, v, and w is going to give you a plane, because you only have 2 independent vectors there. You don't have 3 independent vectors. Does that make sense? To answer your question. Yeah, it's still a linear combination of U and V. Yes. It's parallel to V in that case. Thank you. Right. If U, V, and W were not all in the same plane, so if U was like that and V was like that, so if W was independent from those guys, the set of all linear combinations would be three-dimensional space. Like if they have three components, it would be all of R3.